Okay, in this video, we're going to talk about constrained optimization. We're going to walk through two different methods for constrained optimization solutions. And then at the end, we'll talk about uh, corner solutions and how to think about them and how to work with them mathematically. So to begin here, we're going to start with a general optimization problem that we're going to see show up quite frequently. So we're going to have a utility function. Call this u, and it's going to take two parameters, two variables. So let's say this is q1 and q2. Then we're going to have some constraint. So you're coming from the constrained optimization tutorial video. So the problem we often see is utility subject to some budget. So here we're going to have y, which is equal to the price of good 1 times the quantity of good 1 plus the price of good 2 times the quantity of good 2. So this is our constrained optimization problem, and what we're trying to do is maximize the utility given our constraint. So we often write a maximum out front. And sort of for completeness, we often write down which variables we have control over. So we don't have control over the prices or the income. Here we just have control over how much of Q1 and Q2 we choose. So we write this under the maximization, the max argument out front. So the first thing to do is to think about what's sort of going on generally with maximization problems, and then we'll come back to the specifics. So as we talked about in lecture on Thursday, you can sort of think of two dimensions here, and obviously we have more than two dimensions. But just for the sake of clarity, we're going to start relatively simply. And let's say we have some function that looks something like this. And the goal here is to find the maximum, which let's just say happens at some x star. Okay. So we want to find x star, and we're going to use our tools of calculus. So the first thing to do, as we all know, is at this point is to take a first derivative. And that's going to find the function which gives us tangent lines. It gives us the slope of the tangent lines at every possible x. And what we know about the maximum, as long as it's happening on the interior, is the maximum will correspond to a derivative with a value of 0. But we also can pick up other points on the function which also correspond to derivatives with a value of 0. So we're going to come back to this a little bit later, how we choose which one of these three is the maximum. And when we think about corners, and let's actually set this up right here at the beginning. When we have functions that look, let's maybe extend this. So maybe something like this, and then we end. So we have a range, and we come to the very maximum, and x stops. So this is sort of our end. This point here is actually the largest value, but the derivative will not be 0. The derivative will actually be positive. So we sort of have to deal with a bunch of these issues in this video. For the beginning here, we're going to ignore these corner solution issues, and we're going to cap our function f on the interval all the way up until we reach this blue line. So this interval here. So the x star that maximizes f, our argmax, happens on the interior, so we're not on the corners. Before we talk about the function we actually are aiming to maximize, let's just set up a two-variable version of what we've done graphically. So let's say we have some function f which takes x and y, and we're trying to find the maximum xy. So we're trying to find some x star y star that maximizes f. And we're going to say x and y are all values on the reals. Okay. All right, so we can write this as max x y of f of x y. So the first thing we'll do is set up our first order conditions. This is just the first derivative of each of our variables that we have control over. So FOCs are the derivative of f with respect to our first variable, x. And we're just going to set this equal to 0. And this is going to give us the slope of the tangent line. The derivative tells us the slope of the tangent line. And we're just looking for all the points on all the points that correspond to a slope of the tangent line in the x dimension that are flat. So this is our first order condition. Call this 1. And our second is just the same thing, but for y. Okay. So these are our first order conditions. And just remember here, we've not said anything yet about, make a little note here. We've not said anything about 1, corner solutions, and 2, about max or min. And importantly, we also haven't said anything about global max. We haven't said anything about global versus local. So you'll notice up above, the first derivative will capture this point, which is on the interval we're looking at is a maximum. The first derivative will also pick up the minimum, but it will also pick up this third point, which is a local maximum. So it's the highest point in some region, but it's not the global max. So our first order conditions here will pick up each one of these three. So we're going to come back to how to sort of distinguish between the three in a little bit, but I'll just make a note that generally in this class, it's going to be pretty clear when we're looking at max versus min. Sometimes global versus local will matter, but a lot of the times the functions we're working with don't have this type of shape where they have multiple extreme points, which in this case we have 3. Typically, they're just going to have 1. So in most situations, the first order conditions are going to be enough to pick up the solution. But a lot of times you'll see multiple solutions, and that's when you should make sure you're looking at a maximum or a minimum, or you're looking at multiple global versus local extreme points. Okay, so this is the setup for what we're going to do next. This is f is some function we've tried to maximize over. But the next set of steps is actually to take our economics problem, this maximizing over Q1 and Q2, subject to some budget constraint, and translate that into a problem we can apply our first order conditions to. So first, we're going to cover what we call the Lagrangian method. And this is covered in the textbook, so I'm going to refer you to the textbook for specific details. This method, the Lagrangian method, is not the one I prefer. It's a very useful method, but it's often more complicated when you're dealing with the types of problems we see in this class. So it's a very useful method, but for budget constraint problems, it introduces an extra variable, and you'll see exactly how this plays out. So we're going to set it up, and we'll talk about some of the details, but we're not going to dive into the full problem in the most rigorous way. But I'll show you how to set it up. So let's say, as we did before, that we have our utility function. So we'll put this up in the corner here. Utility function Q1, Q2, subject to some budget constraint. So y is equal to Q1, P1 plus Q2, P2. And we're trying to maximize. Okay. So the analogous function to this f that we have set up in our demo problem is we often write this as this sort of script L, and the L is coming from Lagrange, who was a famous mathematician who developed this type of approach. So the idea with the Lagrangian method is that we have the utility function, which goes into the function we're aiming to maximize. But we also introduce this new variable, which there are interpretations for what this lambda is doing. Essentially, this tells you something about how important, how valuable an extra dollar is. So there is some interpretation here. I'm not going to talk about everything that's involved here. We're going to gloss over most of the dirty details. We're just going to talk about how to set this up. So here we have the budget constraint, and we're just going to set this equal to 0. So essentially, we're not introducing anything else into the problem. We're saying this lambda is multiplied by some 0, by 0. So we're not changing the utility level. But instead of writing the budget constraint as it's written here, we can actually rewrite this. We can say 0 is equal to Q1, P1 plus q2 p2, and then we're going to subtract y. And this is what goes into this bracket here that we're multiplying by the Lagrange multiplier, the lambda. So here we have q1 p1 plus q2 p2 minus y. Okay, and we're treating y as a constant. It's not something we have control over. So this is the function we're aiming to maximize. But here we've introduced a new variable, lambda. So our first order conditions are three. First is q1. Oops. Write this out, first order conditions. The derivative of this function with respect to q1, we're going to set that equal to 0. The derivative of the function with respect to q2, set that equal to 0. And the derivative with respect to our Lagrange multiplier. And again, we're going to set that equal to 0. And at this point, all you have to do is take derivatives and use your knowledge of systems of linear equations to solve for each of the variables. So I'm going to write this out generally. I'm not going to go through and solve it, but this is the setup. So here we have the utility, the derivative of the utility with respect to the first argument, which is here. And this is the second argument. Then we have our Lagrange multiplier times q1, or excuse me, p1. We're just, the rest of what's in the parentheses doesn't depend on q, so all we're left with is lambda p1. And that's all, that's everything involved in our optimization function that's related to q1. So next, we're going to do the same thing, but for q2. It's going to look very similar. So we have the derivative of u with respect to the second argument plus lambda p2. And thirdly, we're just left with the budget constraint. So this is q1 p1 plus q2 p2 minus y. And then, of course, you can rearrange this. Okay, so this is the whole setup. And there are a couple tricks. You can take, you can solve both of these in terms of lambda is equal to something and set them equal to each other. And that's going to give you a nice relationship between the marginal utilities. And this is actually going to look a lot like MRS, marginal rate of substitution, equaling the marginal rate of transformation. Okay, so I talk about all of this just as a note, sort of as the idea for the steps we're skipping. The second method is what I think most people use in economics. It's what I use most of the time. It's what the people I spend most of my time with use most of the time when approaching these types of problems. And this is called the substitution method. So where above we were actually introducing a new variable, this Lagrange multiplier, we're going to do something slightly different. So we're going to have our utility function, u of q1 and q2, subject to some constraint, which is y is equal to p1 q1 plus p2 Q2. And then we're going to try to maximize this. Instead, we're going to combine both of these functions into one. So the first thing to realize here is Q1 and Q2 are related through the budget constraint. So this tells us a line that we must live on. So what we can do here is just solve for Q1. So I'm going to bring P1, Q1 to one side, and we have Y subtracting P2 and Q2 from both sides. And then we'll divide both sides by P1. So this gives us Q2, P2, Q1 is equal to Y minus P2, Q2 over P1. Now, this is a relationship that must be true for our optimization problem. So what we can do is take this and plug it into the utility function, which reduces the problem to one dimension. Sometimes people call this reducing the dimension of the problem. Here, we're just calling this the substitution method, just as a shorthand. But we've essentially restricted what's possible in the utility function according to some line. There are ways of visualizing this in higher dimensions, but essentially we're just slicing the utility function according to the budget constraint. Okay, so our problem now becomes maximizing over the utility function with Y, P2, Q2, P1, and Q2. Okay. So now all we have to do is take a first order condition with respect to Q1. Q2. So we have the derivative of, and we can write this as maybe a non-script L, the derivative of L with respect to Q2, and we're going to set that equal to 0. So just to write this out, we have using the chain rule, we have the derivative of the outside. So we have two arguments still. So we have to take the derivative of u with respect to the first argument. So this is u1 times the derivative of the first argument with respect to q2. So that's just going to be negative p2 over p1. Because y doesn't depend on q2, so we can ignore that. All we're left with is the negative p2 over p1 times the q2, and the derivative of that is just negative p2 over p1. Okay, so next we have the utility of the second argument with respect to q2, and that just comes out to be the slope, the derivative of the utility with respect to the second argument. Okay, and this is much simpler than what we had above. Instead of having three derivatives, we just have the one, and it turns out the solution is identical, which is a property we much love. Okay, so all we have here is just bringing this first part to the left-hand side, we have P2 over P1 times the derivative of the first argument, which is equal to the utility, the derivative of the utility with respect to the second argument. And just to rewrite this in its final form, this is P2 over P1 is equal to U2 over U1. And this is, we could also write negatives out front if we cared to, which then gives us MRT is equal to MRS. Okay. So this is the solution to the consumer's problem in its general form that you've seen before and will come to know and love. So what we're going to do next is actually walk through an example problem. Okay, so let's say the utility function looks like this. We have u is equal to 8q1. Let's write this as little q to the 1/2 power plus q2. So this is not a Cobb-Douglas. And we have some expenditure and we have price 1, price 2, plus price 1 Q1 plus price 2 Q2. Okay. So using our general solution here, we can skip a bunch of the steps. So let's write this out. So another way of writing this is that the utility function is a function of Q1 and Q2. So our utility of the first argument is the derivative of u with respect to Q1. And that's just going to be 8 times 1/2 times Q1 to the negative 1/2. And our utility of the second argument is the derivative of u with respect to Q2, which is just 1. Okay. So here, we take the ratio of the two, u2 over u1. And you'll notice it doesn't actually matter which, whether we have subscript 1 or 2 on top. We could have gone through the math and done everything the other way. So I'm actually going to rewrite this. It's going to turn out to be a little easier here. I'm going to rewrite this as 1 on top and 2 on bottom, which means because the derivative of the second argument is just 1, so all we're left with is just 8 times 1/2, which just gives us 4, times Q1 to the negative 1/2, and by our MRS equal to MRT, we just have P1 over P2, which this allows us to solve for Q1 in terms of prices. So we will use some numbers in just a second, but for now, we're just going to use the variables. So this is 1/2 times 1 over 4 P1 over P2. Okay, and then we're just going to multiply both sides by, we're going to raise both sides to the -2 exponent. So we have Q1 is equal to 1/4 P1 over P2. It's -2. And we'll use star to denote that this is the solution. So we'll just distribute. Some people prefer doing this a different way. Whatever solution method you prefer is the correct one. Okay, so we have 4 squared plus P2 over P1 squared. So this, just erase this and write it as 16. Okay, so this is our solution to the consumer's problem for quantity 1. We're left now with a problem. What do we do? How do we solve for Q2? We're not told anything about Q2 from the derivatives. So the next step here is to use what else we know about the relationship between Q1 and Q2, and that's the budget constraint. So from before, we had that Q2 is equal to y minus P1 Q1 over P2. And what we can do is substitute in our value for Q1 star into this relationship, which then gives us Q2 star. So let's just write this out. So we have y over P2 minus P1 over P2 times Q1, which here is 16 times P2 over P1 squared. And this is going to cancel with one of these two, which just leaves us Q2 star is equal to y minus P2 minus 16 times P2 over P1. All right. So let's plug in some numbers here. Now that we have these parametric forms for Q1 and Q2, let's say income is equal to 12. Price 1 is equal to 2, and price 2 is equal to 1. Here, we can just take our values and plug them into our two relationships. So for the first one, Q1 star, that's equal to 16 times 1 over 2 squared, which is 16 over 4, which just comes out to be 4. So let's box this. Q1 star is equal to 4. For the second one, plug in 12 over 1 minus 16 over times 1 over 2. This is 12 minus 8 comes out to be 4. So we also have Q2 star equals 4. Okay, and that's the solution. We have input values for our parameters, which then give us the solution to the optimization problem of the consumer. Okay, let's finish up with corner solutions. So this gave us a nice interior and unique solution. So this is unique and interior. It's unique because there were no other possible solutions, and it's interior because both Q1 and Q2 are positive. Okay, but let's try a little example that isn't so straightforward. So instead of looking at a price of 2 and 1, let's set this up as a price 1 is 2 and price 2 is 4. Income is equal to 12. Everything else in this problem is going to be the same. So we can actually use the solutions from before, and we'll box these in blue just to make them stand out. And we'll just essentially copy them below. So the first one, Q1 is equal to 16. Q1 star is equal to 16 times P2 over P1 squared. Just double checking. And Q2 star is equal to y P2 minus 16 P2 over P1. Okay. So our problem here is just essentially plugging in the numbers and solving for the quantities. So first, for Q1, we have 16 times the ratio 4 over 2 squared. And this just comes out to be 16 times 2 squared, which is 4. And that's just Q star 1 is equal to 64. Okay, so for the second one, and this is where things will get a little less straightforward, is we have income of 12 over P2, which is 4, minus 16 P2 over P1 is just 2. So this comes out to be 3 minus, and this is 32. So this comes out to be a very negative number, 29. Okay, so this is our Q2 star. Okay, so what's going on here? Is this a solution? Well, it's not. We can't have negative quantities, at least not in our setup. So to dig a little deeper in this problem, one trick is to actually take the utility function and just plug it into Wolfram Alpha. It's a great math computational engine. It's really handy when you're trying to visualize mathematical objects. So I just took the utility function and plugged it into Wolfram Alpha, and we get something we call a contour plot. So I'm just going to draw this roughly out on the screen here. So we have x on the horizontal, y on the vertical, and you can get this. You can get the contour plot or the utility function in 3 dimensions in Wolfram Alpha. But another way of visualizing this is with the contour plot, which is essentially, it's just going to create indifference curves for you. And roughly, this isn't going to be perfect, but roughly what this looks like is something like this. And these are for different utility levels. So we call this U bar 1, U bar 2, U bar 3. And what the budget is doing is drawing a line X and Y are a little confusing, so let's write this as Q2 and Q1. And what the budget line is doing, as we've visualized in videos, is actually just drawing a line like this. But what you'll see here is as we continue to move up the indifference curves, and depending on the slope, we can actually end up with tangency points that lie below the positive values, the negative Q1. So we can set this up in a way where this point of tangency, where MRT equals MRS, gives us a negative value of Q2. And that's exactly what's going on here. We've set up the Y and the prices in a way where the tangency gives us a negative value. So the solution to this is actually a little bit more complicated. Because we can't have negative values, we're pushed towards an extreme point, which is what we call that's maybe the wrong terminology. We're pushed towards a corner solution, which happens here. We would like to be here, but we're constrained by the corner, by this little corner here. So we can't sort of get beyond this because we bump up against 0. So we know we would like to have negative quantity for 2. We can't do that. So the closest thing we can do is 0. So to solve this, we actually have to plug in Q2 star is equal to 0. We're essentially bounding from below, or restricting to just the positive values. And there is a way to do this with the Lagrange approach, introducing 2 more Lagrange multipliers. But this is the sort of the simpler version, where we know we want to be on the negative side of Q2, but we know we can't feasibly achieve that. So we have Q2 is equal to 0. We take this Q2 equal to 0 and we plug it into our budget constraint. Y is equal to P1 Q1 plus P2 Q2. But this is equal to 0. So all we're left with is full expenditure on Q1. So Q1 is equal to Y over P1. And this gives us 12 over P1, which is 2. Gives us 6. Okay, so Q1 is equal to 6. Q1 star is equal to 6. Okay. So that's what's going on with these corner solutions. Okay. And the reason we were able to do this is because we had a utility function that allowed for a point of tangency uh, below uh, the positive quadrant. And that's not always the case. And with the Cobb-Douglas, you were able to see in the tutorial video that it actually looks more like this. And we can get closer and closer to the extreme points, but as long as we don't deal in negative numbers, we can't actually get a point of tangency that lies with one q positive and one q negative. But of course, if we were to plug in two negative values, we can end up down here. But our solutions aren't really going to allow us to see those, at least as clearly. Okay, so I think we're going to leave the video here. Feel free to send me questions if you have any. We'll talk about this a little bit in class on Tuesday. And good luck.